Once again, welcome everyone on DataOps Poland meetup. Today we have the OpenSearch, and David is our guest and will be our star. So David, you can share the screen and your turn.
All right. Let's see. Thank you everyone for having me. Also, we definitely need to get OpenSearch. Yep, it's coming. Sorry.
Yeah, great.
There we go. We also need to get OpenSearch on that DataOps Academy. That would be phenomenal. But hi everyone, I'm David. Today we're going to be talking about finding the right things with OpenSearch. So you guys are all data junkies. You know how difficult it can be to find what you're looking for, whether that's in a database, whether that is in a log store. So we're going to talk a little bit about finding information retrieval kind of as a subject. So a little bit about me. If you'd like, you could connect with me. That's my personal link tree. I have been a data engineer. I've been a DevOps engineer. I've been a network engineer. I've done process automation. I've done a lot of different things. And that's kind of helped me to see that like everyone has these kind of issues around finding the right things with their data. So what is OpenSearch? For those of you who may not know, OpenSearch is a community-driven open source search and analytics suite derived from Apache 2.0 license Elasticsearch 7.10.2. So basically, we forked Elasticsearch at its last open source offering, and we're spinning it into what I would describe as something that's going to be probably very different going forward. So initially, our code bases were really similar, but we're starting to do a lot of things like decoupling plugins so that you'll be able to add plugins on the fly. OpenSearch itself is a daemon, so it's the search backend. Then there's OpenSearch dashboards, which is a web-based UI for like visualizations. There's going to be an admin panel coming soon. Does all sorts of different things. And then there is a boatload of like plugins, client libraries. So whether you want to integrate to Hadoop, we're doing a Hadoop integration. Same with Flink, Apache Flink. And I mean, the list goes on because every database is good for what it's good for. And OpenSearch brings the search and analytics to a lot of different data stores. And I think the biggest thing about OpenSearch is it's open source first. So all of our features are getting developed in the open. Our community is contributing to it. So yeah, with that, let's start talking about what OpenSearch is used for. So it's primarily three, I would say, main areas. So observability, which is, of course, you have a log and you want to search for that log. So you dump those logs in from 10, dozens, hundreds, thousands of servers into OpenSearch. And now you have this central place where you can like find all of your logs and understand what's happening on your infrastructure. If there are exceptions, if a service has gone down, if a server's gone down. So that's the observability portion. There's security analytics. So that is, we have all of these security events that get ingested. And you can do things like, hey, is there someone malicious on our network? Are there malicious devices on our network? Are we vulnerable to different things? So all of these security events can be ingested into OpenSearch and then used to figure something out. And the last piece is that enterprise search. So this, for anyone who doesn't know, that is just like document search. So I go on, Amazon.com and I want to find a Sailor Moon tee. Well, I'm not looking for a T-shirt with, a sailor, yo-ho-ho, a moon. I'm probably looking for Sailor Moon, the anime, on a T-shirt. So that is the enterprise search space. And all three of these things have one thing in common, and that is they're search problems. You have to find documents that are relevant to you, whether it's the log that you're looking for that contains the error or exception, whether that's the right security event that's going to tell you that someone's on your network, or whether that's a document that says, hey, here's the product, here's how much it cost. and so forth. And so how do we find these right things, right? You've all been on a website or something before, you're executing some query and you're like, why can't it just find the document I'm looking for? I know what I'm looking for. I'm trying to tell the search engine what I'm looking for. So OpenSearch has a couple tools to help you tune and find documents that are relevant to you. So what is search relevance? It's the measure of the relationship between your query and any particular document or set of documents. So when I type a search in, I'm looking for, right, Sailor Moon tea. I have something very specific in mind, and that should hopefully bring back the right documents. So, of course, there is a way to do this, and it is with awful math. I feel like everyone don't leave all at once. I'm serious. We will get through this. So OpenSearch relies on this function, which looks really scary. It's called BM25. It's the core search relevance calculation, and it gives a score for how relevant this document is for this query. For those who are wondering, it's actually OCOMPI BM25, but BM25, which stands for better match, and it's the 25th attempt they made. So let's get into this real quick. I say real quick. Let's get into this and make it a little bit less scary so we can understand how these documents are scored. And then we'll talk more about what does this do for us? Like, how does this help us find relevant documents? So to start, we're going to be scoring our document, D, against the terms in our query, Q. And for every term in our query, this little sigma here that everyone can see, that is basically just a fancy for loop. And it says for every term over our query, just add the scores together. So for each, add the term score to the total score. So to start out with, BM25 takes in the frequency of the term in a document. So I type in a query, we'll say Sailor Moon tea, and it's going to go say, all right, sailor. How many times does the word sailor happen in this document? And we have an example here. So here is our wonderful index. It has 3 documents. And we are going to be looking for the words bit and down. So in document 1, down occurs 2 times. In document 2, it doesn't occur at all. And in document 3, it occurs once. So far, we've got term frequency of 2 on the first doc, term frequency of none on the second doc, and term frequency of 1 on the third doc. And if we stop there, doc 1 would look really great. But we're also looking for the word bit. So document 1 has bit once, document 2 has bit twice, and document 3 has bit also twice. Here we go. Now we have some scores. Problem is, if we just look at term frequency, that's not going to get us very far because we've already found ourselves in a tie situation. So before we get into that, which I organized my slides in a confusing way, and I apologize, but we're going to talk a little bit about something called term saturation now. So a lot of times you'll have documents with repeated words. Here we've got down, down, bit, 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 and then the lyrics to a popular song, we're going down, 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 down. Sorry for subjecting you all to this. But we can see down is repeated a ton of times. Does that make it a ton more relevant? No. They just use that word over and over again. And it doesn't mean that much more because they repeated it 100 times in this document. So that's where the next part of BM25 comes in. That is our magical K. K is a constant value. We apply it the same every time. In OpenSearch, it defaults to 1.2. Not that you need to remember that because OpenSearch does. But that lets us tune how much a document getting repeated is important. And I think this next graph will help show us. Yeah, here we go. So say, for example, we add that k in, and if k is 1, well, a document getting repeated or a word getting repeated a bunch of times in a document, that's fairly important. We can tune that all the way down, though, so that, every time you add a new instance of that word, it's not that much more relevant, right? We see 4 is a lot less aggressive. It's a very slow climb, and it tapers off much faster. So that's to say that, hey, this is our way of adjusting, like if a word is repeated a ton of times, it either is or is not going to affect that score very much. There's another problem. Say we have, again, our index with our first 2 documents, and then we have document 3. Document 3 is ridiculously long. This could be, maybe you got a log that has an entire stack trace, right? One word out of that document, say it's 300 characters long, doesn't actually make that much more relevant, right? We say the document's longer, so it should be less relevant compared to the overall length of the document. So that's where our, let's see, yeah. Also, just to point out, this document would have the exact same score despite being 300 words long. That's where we add the document length into. So we have the length of this document, which is that D on the top, right there. And then we divide that by the average document length. And that helps us normalize, hey, it had this many, or this word, but it was like a ridiculously long document. So like the word down, say, for example, it only had down once, but it was 300 long. Now it's going to be 1 over 300 versus our first document, which has down twice, which is 2 over 15, because the first document's 15 characters long. You have to trust me on that one. So 2 over 15 is obviously going to give it a bigger score than 1 over 300. So that's our way for like normalizing, hey, maybe this document is ridiculously long. Like we want to adjust for that. And of course, everything needs to be tunable. So we have this magic sauce here, 1 minus b plus b times the doc length over the average doc length. That's just a little knob. B is one number between 0 and 1 that lets us say, hey, maybe for us, this actually doesn't matter that much. Say you're a bookstore. Books come in all different lengths. So you could have a book that's 100 pages long. You could have a book that is 10,000 pages long. So you can make that more or less relevant. Again, OpenSearch ships this by default as 0.75. All right. It's a lot of math so far. We're getting there, I promise. So, oops, helps if I'm clicked into the right place. The last part is called inverse document frequency. So say, for example, a word is repeated in every single document. Is that word very relevant to your search? Probably not. Take, for example, the word the. It happens in just about every sentence in the English language. Is the word the really going to make that much more of a difference? If the happens 100 times, 200 times, if it's in every document is going to be getting scored based off of a word they all share in common. So this last thing adjusts for that. And the way that it does that is it takes the number of documents. So in our index, we have 3. And it divides it by the number of documents with that term. And we add 1 at the end to make sure it's never negative. And I'm going to be completely honest. There is a reason for n number of documents minus number of documents with this term plus 0.5 plus 0.5. It's something fancy and mathematical. And overall, it doesn't play that much into our scoring. So we're just going to leave that to the side for now. So here, let's do an example end-to-end calculating the BM25 score. So we've got our query with the words bit and down, and we're just going to score document 1. So document 1 has down 2 times. Document 1 has bit 1 time. And it is 15 characters long. 15 words long. And let's go into the math. Now, you don't ever have to worry about this, thankfully, but here we'll walk this side to side. So we're looking for the score of our first document, document 1, against the query with the words bit and down. So we first start by scoring bit. The word bit occurs once, that's its frequency, divided by 1, plus our 1.2, which is our magic number. We have our magic special sauce. Its document length is 15. The average document length for this index is 13, times the log of, we have 3 documents. And this is actually one of those places I'll stop for just a second. So we have 3 documents. All 3 of the documents actually contain the word bit. So bit is actually not going to play that much into the effect of our score for this. So we've got 3 minus 3 plus a half over 3 plus a half. That's going to be 0. So we've got a half over 3.5 plus 1. Take the log of that, and we end up getting a score of 0.06. Is 0.06 a good score? It's all relative to the other documents. So we also, because of space, I just wrote the BM25 score for the word down. So you calculate all this for the word down on our first document, and you get 0.28. That's much more important and relevant because the word down only occurred in 2 of our 3 documents. So here you can see just how this kind of comes into play. And for this total, we get a total score of 0.34. That is how OpenSearch looks at documents and says, hey, this is more relevant, this is less relevant. So we've got our final scores. Doc 1 was 0.34. Doc 2 is 0.08 because it only contained the word bit, and it contained the word bit more than once. So our previous document had 0.6 was the score because bit only occurred once. Here we can see bit occurred twice, but it only added 0.2 more because bit occurred in every single document. You don't ever have to worry about remembering this though. But we have explain equals to true. So explain equals to true does everything I was just saying and just tells you what it scored all the documents as. So that's really helpful if you're like, hey, why, I've entered all these words into my query and like some random documents floated to the top. What's going on? You can use explain equals to true at the end of or inline your query string to start understanding like why did this score the way that it did. And that helps you dive down on like, what terms were or were not relevant, and then you can start tweaking. Now, this is all very cool. That only applies to each field. So each field is going to get scored, and those field scores get pulled together. And that is where search relevance comes into play, because this is just a single score. And scoring isn't the same as relevance, right? This gives us an approximate number that we can start tuning to figure out, hey, were those documents actually relevant? So relevance has 2 parts. On the one hand, it's precision. And on the other hand, it's recall. And they're related in an interesting way. As your precision goes up, your recall typically goes down. As you increase your recall, you decrease your precision. So let's get into what both of those mean. Precision is the score of the number of true results that you got back that actually were a match for your query, divided by the true positives plus any false positives you had. So say, for example, we had the perfect world. We would return all of the documents that we wanted to see and none of the documents that weren't actually relevant. And our precision would be 1. That, of course, can't be the case because we are people. We write spelling errors. There are typos. There are words that mean the same thing, but could be 2 different words that mean roughly the same thing. So we do need to increase our recall and decrease our precision so that we get all of the documents that we're looking for. So we're going to take a quick minute and look at what types of things affect our precision. So in OpenSearch, we have the match phrase, Boolean queries, and boosting fields. These are three kind of core search types that can help you tune your precision. And we'll go in and we'll do some examples. If I can four-finger swipe, there we go. So as I mentioned earlier, we have our explain scores. If anyone wants to drop in the chat as well, if this is too small of text, I'm happy to zoom in a little bit more. But here we have some sample index, flight data, and Osaka. We can just say, hey, what are flights that match the origin city name of Osaka? And here we can see, oh, look, here it is. And this is why it is what it is. So say, for example, IDF here, it says for this document was computed as the log of 1, da, 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 da. And that's our BM25 that we were just talking about earlier. So we mentioned precision. Let's go down here. So the first one is match phrase. And this could be, described as match exact phrase. So here we have an e-commerce data set, and we're just going to search that data set. And we're going to do the match phrase type search where the manufacturer is equal to low media. Nothing's returned. And the reason for that is low media doesn't actually exactly match any of our documents. And this is one of the interesting things that I was talking about with recall, right? Low media does exist somewhere, but it doesn't exist anywhere as an exact match. So this is really great if you know exactly what you're looking for, like you're looking for an exception, maybe it's a named exception, you can go and find that. But unless you get it exactly right, you will not get the results. So we can adjust that with slop. And slop says, hey, one of the tokens in our phrase, so low media, cannot match along those lines. So here, say, for example, we've added slop equals to 1. And all of a sudden, we get a boatload, 1,500 documents. And that's because it wasn't low media. Oh, I forgot. It's low tide media. So again, adding slop, it decreased our precision because we were looking for exactly low media, and there was no exact match. But low tide media does match. Andrea, I think you raised a hand.
Yes, this is very, very interesting, especially the way it's formalized as a REST call. But what about if I am one of my users that are using OpenSearch and are not performing those queries via REST, but rather via discovery and query? Do those things apply? And if yes, how would I be able to run things like match phrase as well?
That's a great question. So there are actually, I was going to say 3, but I think there actually might be more. There are a lot of ways that you can query against OpenSearch. So this is using our, oh gosh, now I'm going to forget the name of it. This is our typical, query language. There is an OpenSearch query DSL. There is a Lucene query language. You can do SQL actually against OpenSearch. And then also you can take use of like some ORMs and things along those lines. So a lot of times what people will do is I'll say the enterprise search world is you'll bring these together and you'll create a whole template. And that template will take in the queries in several different areas and use that to score or tune the score. So say, for example, I'm just going to put this in mustache template. So you might, on the back end, have a web app that does your queries like a mustache, and this, I think it's $mustache, and then search phrase. That would take, their single query, and then you can start adding and layering these on top of one another to create a more relevant experience. And this is actually a big field. It's called search relevance tuning. And That's how companies like, Shopify help users to find the right things. Is they tweak with some of these things, and then they measure the results out in their production environment. Say, hey, did we end up with more people getting to their destination, we'll call it. So an example would be like, I searched for my Sailor Moon tea, and it was the first result. I clicked the first result. That's perfect, right? That is best case, but that doesn't necessarily happen, right? We search for Sailor Moon tea. There are 50 different examples, and they will tune against several different things. So how much does title match matter? How much does the body matching matter? There are other things you can do as well. Like one of the interesting things that a lot of people find in the search relevance world is the number of reviews is more important than the overall review, stars, we'll say. Say, it's a 5-star scale. A document having more reviews with 4 stars actually more often than not is more relevant than a document with fewer reviews and 5 stars. It's very interesting. So those are the types of things you can start adding into these templates. And unfortunately, I was just thinking before, I need a slide on templates. I have a place I can show you, but we'll dig into that a little bit more further. So with that, we've got, our match phrase, this is an exact match. Let's look at our Boolean query. And this is where you kind of start to add those layers. So here's our sample e-commerce data again. We've got now 3 different, we'll say, top-level query items, we'll say. It could either, it must have something, it must not have something, it should have something, which must is a little bit like an and operation. Must not is a not. And should would be like an or operation. And then filter is very interesting. This can actually speed up how quickly you get results back, because you can actually filter out a large set of documents first. So first the filter is applied, then it goes into some of the conditional matching. So here, for example, in our e-commerce, we were trying to match, the currency is equal to the euro. This returns nothing because you can't just leave these hanging. So here, this is where I was kind of talking about that layering, right? So you can start and add, these might be a pick list of filters that you could do. So we have a query that must include either the GeoIP region name of New York or Dubai. So from my pick list, I might say, hey, I want to look at either logs in New York and Dubai. I want to look at orders that are shipped from either New York or Dubai. And because this is a should, it's an either or. So we will return all the documents containing New York, all the documents containing Dubai. And if we run this, and I've got my little explain flag here too, we see, look at that, 1372. If I put this inside of a must, we should get nothing back, I believe. Yep. Because GeoIP region has a cardinality of 1. It only ever has 1. So that is where should comes in. It is our or operation. And you can get as deep as you want with this. And this is a really keen point for why we have, ORMs and why we have these ways of generating stuff with whether you're doing SQL or you want to do it in templates, because they can get very deep and complicated. Here is another example of the nested Boolean with our filter. So we've added filter where the destination country is Japan. This is some flight data. Boop. There we go. Now we can see all the flights that are coming in and out of Japan. Sorry, destination going into Japan. We have 774. And the last area that we're going to talk about that really is where precision is tweaked is with boosting fields. So say, for example, we might have 2 fields that have similar data or adjacent data, like maybe title and description. you can actually boost or query against both of those fields and then boost one over the other. Like say, for example, I like Sailor Moon teas. I'm sorry. It was a really good reference. There was a Shopify talk where they talked about the Sailor Moon ring and how people kept getting moon rings and then Sailor rings, but they wanted a Sailor Moon ring. So that's why I keep bringing that up. So here, I might look in the title and say, hey, if I match in the title, that is really important. So I'm going to boost matches from the title versus the body. You know, the body could be tens, dozens of words long, maybe even hundreds of words long. So maybe matches in the body aren't that relevant. So boost with this little caret allows you to apply a multiplier. So matches right now to the customer first name field are twice as relevant as to the customer full name, because if his last name was Kamal, maybe that's not who we're looking for. We're looking for someone who goes by Kamal as the first name. So here we can see, there we go. We've got 69 people named Kamal. So that's boosting precision and tweaking that. Let's talk about relevance now. Or sorry, recall. I keep using those interchangeably. Recall is very different from relevance. So recall is the number of true positives over the number of true positives plus false negatives. So this is, when we queried, did we get all of the documents that we expected? Or were there documents missing that actually should have been included? So a good example for why we might be missing documents. Maybe we've misspelled something. Maybe we spelled something approximately how we think it sounds. Maybe there's another word that describes what we are looking for that also matches. So recall, more often than not, is going to increase the number of documents returned, whereas precision generally trims the number down. And I kind of alluded to this, but here we have synonym matching, we have some fuzzy matching, and we have phonetic matching. So let me dive into some examples of those real quick. There we go. So we talked about synonyms. I think we're all data engineering type people. We're familiar with servers, containers, etc. So I might search for EC2 instance in my logs, but it might be logged as server. So this is a way, and I'm going to say query side because there is also a way to index with synonyms, but we're not going to cover that today because it is a very long topic and we could go on and on forever. But you can look for synonyms on the query side and on the index side. What this does, it'll actually substitute instances of this word with or. So say, for example, say I look in EC2, it's going to look for, let's see, also this comes in as a template. So if I type in, EC2, it'll look up EC2 or server, which could be really helpful, right? So say, for example, my server, it doesn't know what instance type it's on. It's just going to say, hey, I'm a server. I'm a web server running wherever you've asked me to run. So being able to substitute those is hugely valuable, but you might get the wrong information. So say you had a query, you typed in EC2, it says EC2 or server. Well, you might get some servers that were running in containers. So it's helpful because it can help us find docs we might have missed, but also it can hurt us because sometimes we're going to find documents that aren't precisely what we were looking for. I mentioned this is a template. So if I click play, this adds this filter graph, which, by the way, you can do like multiple lines of these synonyms. You could do, say, I'm going to pause and just think about this. Let's say Python, and it might say, hey, if it's a PyPy error, PyPy, oops, there we go. Those might be the same things. So this adds it to OpenSearch. And then when users query against logs, it will use this synonym graph to expand their query into all of the different relevant synonyms. And it happens automatically. The reason you might do it server-side on ingest is maybe you want quicker response times. If you do it on ingest, then the response times will be quicker. If you do it here, you might have slower response times, but you have much more flexibility because you don't have to re-ingest to get new synonyms. Philip, you had a question.
Yeah, I wonder if we can ingest, because you were ingesting variables into this query. I wonder if we could, for example, a huge file or even database with the synonyms, like 1 billion of synonyms. We could I'm not sure if this is reasonable, but could we ingest these synonyms into this query from outside of the query?
Yes. So that is a super good question. And I would do that if you're going to do that and you have a very large synonym document, which a lot of people do. I would do that ingestion side. And the reason for that is if you do it query side, you could end up with so many expansions that it could make your query take forever. If you do it on ingestion side, it's going to take up more storage, right? It's going to expand those out on the document itself. But when you query for it, it is much quicker. But it's a long process. And if you ever make updates, you have to then re-ingest all of your documents through. And that's some of the trade-offs that you'll take, whether you do it query side or whether you do it ingest side. So.
Yep, thanks.
Yeah, for sure. And there are dictionaries out there that exist. And, for each domain, you're going to have different synonym lists, which is really interesting, So like observability, you might have different synonym lists. You might even get as narrow as a Kubernetes specific synonym list. So then we have fuzziness. So fuzziness allows us to mistype something and still get a word that is approximately close to this. And I actually have my friend Liza, who also talks a lot about OpenSearch, to thank for the understanding on this one. It uses something called the Levenshtein distance, which is a concept I have no clue about. But that's okay. We don't have to know about it to be able to use it, thankfully. So here, for example, we're looking at our flight data, and we have Osaka, which is incorrectly spelled here. We have auto fuzziness on, though, so it goes and it finds us, oh, look, origin city name matches Osaka. And that is because the Levenshtein distance for this is close enough to where it's like, okay, you typed this, that also could match this. It uses trees and matching algorithms. It's very cool. I just don't understand it completely. So say, for example, this, if we wanted to as well, we can manually specify the Levenshtein distance, which this one actually turns out to be 2. And I believe that's because it has an additional character, so the characters are also shifted. But if we set it manually to 1, we could not end up showing it. And that hurts our recall because all of a sudden we're missing documents that should have been returned. So Auto does a good job of figuring out, hey, what's a good approximate Levenshtein distance to be applied. And then the last part, and this one is really actually kind of handy, is, say, for example, you have a million ways to spell the, name Caitlin. Caitlin actually, if I'm remembering correctly, has, I think, 175 different spellings. So you can use what's called a phonetic plugin. And the phonetic plugin takes and it turns words into approximately what they sound like. I don't have a good example for this, but we can analyze the results by trying to ingest these couple words and looking at them. So we have Alexander. This also is probably pronounced Alexander. And then we have Alexander. So let's look at what the outputs of these are. So our first word, Alexander, returned A425, which is how it encodes this. That is the same encoding for the second, A425, because those words sound similar. So it applies similarity algorithms and phonetics. Again, fancy math people, more fancy math than I had time to learn for today. But and now if we looked up both of these, though, it would return the same person versus Alexander, which is a very different pronunciation. So it still has the same ending root, which is why we end up with 425 as our root, or not root. I don't know what the right word for that is, but that's okay. And again, this is a way of like approximating, like, hey, how does this word sound? Like, do we find similar sounding words? So this is a perfect example of that, because names can be very tricky to spell. The caveat here is if you know that your person spells their name Alexander, and this goes into, a phonetic search field, and you look that up, we might return the wrong Alexander. So this is where you could say, hey, I'm going to boost the actual first name field, but if there's a match on the phonetic first name field, I'm also going to include those. So they might come up lower than exact matches, but you still get them. And that is all I have there. So that is recall. So now I mentioned, these are all tools that you can use. You can start adding these rules together to start tuning for your data set. Like, hey, how much boost do we need to put? When we tweak the boost up 2, 3, 4, do we get more correct results, or are we just getting a bunch of garbage? And this applies everywhere, whether you're looking at logs, security events, whether you are looking at, document search like books or text, or, whatever the use case may be, you're going to want to ingest your documents a couple different ways so that you can search for them and get the right things. With that, I mentioned there is an example. This is somewhat what a template would look like, and I apologize, the text is very small. But this is that little mustache template that you can use. And it can enter in the search text in several different parts. And this is our search comparison tool. So on the fly, if you wanted to, you can look at the search cup against 2 different queries, maybe even different indexes, because maybe you've used a different indexing pattern for one versus another. And then see the results side by side. And this is a really good way to do tuning, because you can say, hey, look, this is how I had it before. I updated it. Did that make my results better or worse? And this is available right now in OpenSearch. The search comparison tool is not generally available, I believe. It's not. That means it's not in its final form, but it is available for use. And there are so many other tools. Like I touched on phonetics. We've got different language modules as well, because Polish grammar is different from English grammar, is different from Chinese grammar. And the same with, say Chinese and Japanese, it's all compound. So you need to understand tokenizing different. So there are different tools for ingesting that different data, but OpenSearch has a lot. So with that, if you'd like to try this, you can go right now to play.opensearch.org. That's what the QR scan is. That'll launch you there, and you can start playing around with OpenSearch. You can play with dashboards, visualizations. You can't ingest your own data, unfortunately, but you can practice some of these queries in the dev tools, which is bottom left, dev tools, and then it allows you to play with the REST API and do some queries against some sample data. So with that, thank you all. And what questions do you have? If there are any other questions.